In this video we're going to introduce probably the most important mathematical operation related to control theory, the Laplace transform. The Laplace transform is an operation that takes a function of a real variable and associates to it another function, this one dependent on a complex variable. So if we have f of t being t a real number belonging t to the R set, then by means of this operation, by means of the Laplace transform, which is denoted by this fancy L, we get capital F of S, that is to say the Laplace transform of f of t, where s belongs, lowercase s belongs to the complex set. We usually call the real part of s sigma and its complex and its imaginary part omega. Notice that f of t is what we have been calling a signal. Remember that we are studying systems and signals, and systems acts on signals. Well, here what we have is a signal, and this is what we can call the Laplace transform of that particular signal. Why are we interested in the Laplace transform? What is it useful for? The Laplace transform is useful to solve problems which are difficult or cumbersome to solve in their original representation. So, for example, imagine that we have some problem, a problem involving the signal f of t, and therefore we are here in the t domain. And this problem is difficult to solve. Well, what we can do is to apply the Laplace transform on that problem, the Laplace transform, and then we have a new problem stated in terms of s. So we are here in the S domain, and these problems happens to be a lot easier to solve than the original one, so we can get easily the solution to this second problem in the S domain, solution in S. And finally we can go back by means of an operation that we call the inverse Laplace transform, and that we'll define in due course, and get the final solution of the original problem, solution in T. So as you can see, instead of going directly this way, we've chosen to go this other way, which is a lot easier. The most apparent example of this comes with differential equations. The Laplace transform turns operations like differentiation and integrations of signals, of functions, into algebraic operations, and therefore the differential equations are replaced after having applied the Laplace transform on them, are replaced by algebraic equations. That is to say, equations involving sums, multiplication, division, this kind of operation, like for example x to the third plus 2x to the squared minus 1 equals 0. That would be an algebraic operation where you don't have any differentiation or integration. So as I said, you can get easily this solution and go back with this solution to the t-domain and get the final solution to the original differential equation. Now that we know what we want the Laplace transform for, we can define it rigorously. Definition. Let's assume we have a function f of t with defined for the interval for t in 0 infinity, that is to say defined for all positive time, and we also have the complex variable s. Complex variable. Then the Laplace transform of f of t, also denoted by capital F of s, is equal to the integral from 0 to infinity of f of t times e to the minus st dt. This is the mathematical definition of the transform. It's important to notice that not all functions are Laplace transformable. The transform exists if this integral converges, and to do so certain mathematical requirements must hold. In particular, there are two requirements on f of t. F of t must be piecewise continuous, and also it must be of exponential order. Well, those two are fancy mathematical conditions. You can go very deep on them on math books, but we're not really that interested on that. We simply will assume that all functions that we will be dealing with in this course do have a Laplace transform.